Okay, so we are obviously in the home stretch now with only 2 weeks remaining. Okay, we're slowly running out of time. Of course, grad is the 20th, unless anyone wants to postpone. How come no one ever says, can I graduate like the Monday? Or no one ever says that. Why? No, but how come we can like write the test? But grad got to be that day. Sorry, little ant. Why? I'm not even going to get into that. Not even going to get into that. Anyway, let's begin. Momentum is a relatively short unit. It is the one unit that is very, very heavy on subscripts. Okay? So the problems look challenging. Like if I showed you an example right now, your mind would just go kind of thing, right? So I have to sort of ease you into it. But when you stop and you boil it down, it's just the subscripts, it's the notation that makes it particularly challenging, okay? So if you slow down, you show your work, Zach.
Oh, I thought you didn't test.
It will go a long way. Okay, so having said that, so we will derive the impulse momentum equation from Newton's second law. That's coming up probably tomorrow. Determine impulse from the area under a force time graph. Once again, we return to that famous, fun little skill of finding the area under a graph. It's the same thing over and over and over. It just means different things depending upon what graph it is, right? So we'll do that again, and that'll be for constant positive or negative force and a uniformly changing force. We will experiment to illustrate the law of constant momentum in 1 and 2 dimensions. We will limit ourselves. We'll probably try to do 1 and 2 together, but it's more of a 2-dimensional thing. It's kind of a group lab. It's not one of those ones where you're going to do a hand-in report and blah, blah, blah. It's sort of more of an experience. We will solve problems using the impulse momentum equation, the law of conservation of momentum, and these are the problem types. There are impulse momentum problems, which I like to affectionately call FAT equals MAV problems, and that will make sense to you in the near future. There will be one-dimensional collisions, both inelastic and elastic, and there will also be explosions. So things colliding, that was loud, and things, boom, exploding. And then we'll do that all over again, except in 2 dimensions. And no, we will not do them in 3 dimensions, I don't think. No, I don't think so. John, can you put your feet down? Thanks. And I will relate the impulse momentum equation to real-life situations with one of my favorite demonstrations, the blow dart demonstration. So we'll talk more about that in a little while here. But first, we have to really talk about what is momentum. It doesn't say define momentum or understand what momentum is, but until you understand momentum, you really can't do anything else. Okay, so that's where we're going to be in. Now, you've got a big giant handout there, right? Basically, the entire notes, everything you need to know is inside this little package. Okay, so this will be sort of your little guide for the whole way here, and we'll end up sort of going through it piecemeal. But if you want to sort of use it as a textbook, then that would be certainly good. You'll notice there's a wide variety of questions at the back, and I got answers there too. So basically, you can use that sort of as your guide here. Okay. Must have running on my laptop. Okay, so after today, this is probably the easiest day you've had in a long time. You'll be able to define what momentum is and calculate momentum given mass and velocity. In other words, solve P equals mv problems. Not on the outline. Okay, it's actually supposed to be taught in grade 10. Most of the time we leave it out and I leave it for grade 12. It's a nice easy grade 12 start. Otherwise, we never really get to it in grade 10. And you forget about it because it's been so long ago, right? Okay, so before we go anywhere, tell me, what does the word momentum mean to you right now? If I said define momentum, John, what would you say? Momentum is? What would you say? Moving? Do things have to be moving to have momentum? Like, I always go back to my filing cabinet because it's got a pretty good mass to it. Does my filing cabinet have momentum right now? No? Riley, why not? Just got a feeling. No force. It's not moving, Jason?
That's mine. That's my.
That's your opinion.
That's my-
Does my filing cabinet have inertia? What is inertia? If I said, Hannah, what is inertia? What would you say? You wouldn't. Okay. So inertia is the tendency of an object to basically continue doing what it's doing. Kind of like a teenager, actually. Actually, most people, in fact. People don't like change. Filing cabinets don't like change. They like to keep on doing what they're doing. If they're at rest, they like to stay at rest. If things are moving, they like to continue moving. It's the whole Newton object in motion stays in motion, right? Well, that's inertia. But momentum is different. And Jason is right. Something has to be moving for it to have momentum. My filing cabinet currently has inertia, but it has no momentum. It must be moving. And it must also have mass. That's what momentum is. Okay, so all I want you to do while I go and I do my test, all I want you to do is read the left-hand side right there. That's all you got to do. In fact, it's going to take me longer to go over there than it will take you to read it. So go ahead and read 7.1, momentum. If you're going to write anything down from today, it's this. Momentum is defined as an object's mass times its velocity. There is no derivation for that. It is a definition. Smart people sat down and said, we need something to describe that quantity that we've got when something has mass and it's moving. And someone said, how about momentum? And I said, good idea. We'll make it mass times velocity, and we'll call it the letter P. Because, yeah, well, they couldn't use M for momentum because M stands for mass. That'd be confusing. M is equal to M times V. So they just picked the next letter in the alphabet, right? Well, that'd be N. Well, N is for newtons. Well, it kind of looks like 0. Let's use P. I'm sure that's how the discussion went. You know what? I don't know. I honestly have I spent an hour once trying to find out why P is for momentum. It's got to do with Newton and Latin and mumbo-jumbo that I didn't understand. So don't ask me why. Momentum is P. Now, because velocity is a vector, when you take a vector, is mass a vector or a scalar? Scalar. When you take a vector times a scalar, what do you get? You get a vector. So here you thought, remember how, like Unit 1, grade 11, I introduced you to vectors, and you thought at the end of that test, man, I'll be glad when this is over, because I don't have to worry about vectors anymore. Well, here we are, the last year of grade 12, and we're back to vectors. They never leave. They never leave. So since velocity is a vector, momentum is also a vector quantity. And once again, we're going to be adding and subtracting vector quantities. Okay, so hopefully you can do that. If you want to read page 277, you can. Here's an example from the textbook. It's on page 277. I'm going to just give you an example question, then I'm going to stop. You guys are going to do some problems. I'm going to see a variety of people. Those people that need to finish the test are going to do that. If you still haven't got the lab in, you might have time for that as well. Tomorrow I'm going to start really right into momentum. Okay, so make sure you're here tomorrow. So calculate the momentum of a 1 kilogram duck moving at 28 meters per second and a sumo wrestler with a mass 200 kilograms moving at 0.5 kilometers an hour as shown. This is from your textbook, Hannah. Okay? You have no example sheet, right? So you might want to write down this example. I don't know. Somewhere. Notes, wherever. This is relatively easy. Calculate the momentum of a 1 kilogram duck moving at 28 meters per second and of a sumo wrestler with mass 200 kilograms moving at 0.5 kilometers an hour as shown. Let's do the duck first. Here's where I'm going to introduce you to the idea of subscripts right away. PD, momentum, duck, is going to be mass of duck times velocity of duck. Now, I don't need to do that. Right? But again, I'm introducing you to this idea of subscripts because when we get multiple things, you got to keep them separated, and the way to do that is with subscripts. So I'm going to start with that right here. So momentum duck is going to be mass of duck, which is 1, times 28, which I'm hoping you can all do in your head, the momentum of the duck is 28 kilogram meters per second. Kilogram from the mass, meters per second from the velocity. Wouldn't it be nice if there was some unit for momentum that wasn't kilogram meters per second? It sure would, but there isn't. Apparently there isn't anyone smart enough to be made famous by using their name as a unit. So they go with kilogram meters per second. Tough luck. Okay. Now what about the sumo wrestler? Now you'll notice the mass is 200 kilograms, but what's the speed? 5 kilometers per hour. Does it need to be in meters per second? It sure does. It sure does. So step 1 is going to be take 0.5 and divide by 3.6. Is that right? Yeah. 0.14 meters per second. And now momentum sumo, mass sumo times velocity sumo. He weighs 200 kilos times 0.14. And what do you know? It's 28 kilogram meters per second. They're the same.
How do we get 0.4?
I took 0.5 and divided by 3.6 and I got 0.14. Kilometers per hour to meters per second is divided.
Oh, wait, yeah, sorry.
Okay.
Yeah.
In fact, it's set up for exactly that reason. They are supposed to be the same. Because I want you to understand that a 200-pound sumo wrestler, who's not a particularly large sumo wrestler, right? But if he's running at half a kilometer an hour, which really isn't very fast at all, right? He's just sort of strolling down the street. If he runs into you, well, that's going to feel the same as a 1 kilogram duck moving at 28 meters per second, which is what? Actually, how fast? 28 meters per second is times 3.6. I got 8.4. No, why did I get two different things? It's 28 times 3.6. Yeah, 100. You get hit by a 1 kilogram duck moving at 100 kilometers an hour, it's going to hurt the same, have the same effect as a 200-pound sumo wrestler lumbering down the street. Okay? Momentum is dependent upon both mass and velocity. Okay? That's the sort of the main idea of that.
Now, it's just a quick question.
Yeah. Does it? Okay. So, if you have a textbook, you can do page 278. There's applying the concepts 1 and 2. If you don't, there are some beginner intro questions here. Not a whole lot. Some of them you will find to be, basically, yeah. Actually, you know what? There's very few of these you can do. As I look at them here. You could do number 7. No, these are all fat equals math problems. All you can do is number 7. So, yeah, you're going to have to do page 278, applying concepts 1 and 2. I will see people individually. I will show people how they did on the test. Those people that need to finish can do that. If you have other things you can do, that's great. Tomorrow, I'm going on, whether you're ready or not.
The ones that finished, were they not that good?
They were fine.
Okay, good.